Hello class, Professor Anderson here. Let's see if we can calculate the electric field of a planar charge using Gauss's law. So what do we mean by a planar charge? What we mean is a sheet of charge. Okay? Put a whole bunch of positive charge all over this whole thing, and let's call that positive sigma. What is that? That is charge per unit area. Okay, so just think about sprinkling a whole bunch of positive charge over that entire surface. What does the electric field look like from a sheet of charge? Well, when we talked about the electric field from a line charge, we said it has to go radially outward. And the reason it has to go radially outward is it was an infinitely long line charge. Here we're going to consider the plane also infinite. So if I think about one little section of this plane, that is going to make an electric field up here that looks like that. But I can grab another little section over here, and that's going to make an electric field that looks like that. And by symmetry now, the horizontal components cancel, the vertical components add, and we end up with an electric field that points outward from the plane. Okay? So when you're going to draw the electric field from a plane, remember it always points normal to the plane. So let's draw it again. Here's our plane of charge. Electric field above is up. Electric field below is down. Okay, those things always point normal to the plane, right? Now another way to think about that is parallel to the area vector of that plane, and we're going to take advantage of that when we draw our Gaussian surface. So let's go back to Gauss's law. Gauss's law says integral E dot dA equals Q enclosed over epsilon naught. All right, we have Cartesian symmetry here, right? We don't have spherical anymore, we don't have cylindrical, we have Cartesian symmetry. It's going to look the same in this planar case. So, how do we take advantage of that? Well, remember our E field is pointing up or pointing down, so we're going to draw a surface that looks like this. Okay. It's a little can. That thing is called a Gaussian pillbox because it looks a lot like what people used to keep their pills in on their bedside. It's just a little sort of small can that takes advantage of the symmetry of the problem. It doesn't have to be rounded sides, it could be square sides, it doesn't really matter because you're worrying about the planar symmetry in the problem. All right. If E is pointing up everywhere, dA for here is also pointing up. dA on the bottom side is pointing down. But then we have to go around the edge, and the edges of this thing are pointing out in that direction. So what does the integral become? The integral becomes an integral over the top of E dot dA plus an integral over the bottom of E dot dA plus an integral over the sides of E dot dA, and all of that has to equal Q enclosed over epsilon naught. What is the integral over the top? Well, the integral over the top becomes E times dA times cosine of 0 degrees. They're in the exact same direction. What about on the bottom? Integral over the bottom, E is pointing down, right? This pink line, this is E. but dA is also pointing down. And so we get E dA cosine of 0 degrees again. Remember, it doesn't matter that they're both pointing down. That angle is the angle between them. If they're both parallel, that's 0 degrees. And then we have the integral over the sides. And you can kind of see what's going to happen now. E dA, whoops, we take the vector sign off once we write the dot product. E dA cosine of what along the sides? Cosine of 90 degrees, because E is pointing up or down, but dA is pointing out to the side. And so that whole term is going to go away. This whole thing is equal to Q enclosed over epsilon naught. All right, let's finish this up. This first one, we can pull E out of the integral. It is constant. And the integral over dA for the top is left. We have E times the integral over the bottom of dA. And all of that is going to equal Q enclosed over epsilon naught, because this last term goes away. Cosine 90 degrees is, of course, 0. All right, let's make a little room up here at the top. And we'll go back up. E times the integral over the top. Well, that's just E times A. If this cross-sectional area is A, then the total area of the top is just A. What about the bottom? Well, the bottom is the exact same thing. That is also area A. And so we get E times A for the bottom. Finally, what about Q enclosed? Q enclosed is how much charge is enclosed in this little region right here. How much charge is enclosed by our Gaussian surface? We told you what the charge density was, charge per unit area. So if I multiply by area, that is the total charge in there. So that just becomes sigma times A, all over epsilon naught. And now you see what's going to happen, right? We've got two of these. 2EA equals sigma A over epsilon naught. We cross out the A, we divide by 2, and we get E is equal to sigma over 2 epsilon naught. Now, this is very interesting, right? Why is it interesting? Because it says the magnitude of the electric field does not depend on how high you go. It's a constant. It's just a number. Sigma is a number. Epsilon naught is a number. Does that seem right? Should the electric field really just be a constant as you go up? And the reason it's a constant is because the plane that we're considering is infinite. So as you go higher up, your field of view opens up and you see more charge beneath you. Okay? So only in the case where it's really an infinite plane of charge will that electric field be a constant above it. Now, electric fields are, of course, vectors. We have to figure out how to put a direction on this. And the way you do it is you go back to the symmetry that we started with in Gauss's law, and you say, all right, the electric field was pointing up, or it was pointing down. And so you do this. It's positive sigma over 2 epsilon naught in this z hat direction. Okay? If z is the vertical direction, then we're going to say it's positive if z is bigger than 0. It is negative if z is less than 0. Okay? This is how you write the electric field of a plane of charge. It's either positive or negative if you're below. All right? Hopefully that's clear. Cheers.